Welcome back to electrochemistry. In part 3 of this unit, we're going to be looking at a voltaic cell. Let's get started. Alright, a voltaic cell, otherwise known as a galvanic cell, is a spontaneous chemical reaction which produces electricity, otherwise known as a battery. A battery is a reaction that's producing electricity. So any of these redox reactions where electrons are moving from one to another, there's oxidation, there's reduction. The movement of electrons is the production of electricity. So we're going to see what a battery looks like on the inside and how much electricity it's going to produce. So we're going to diagram. To diagram means to draw a picture of an aluminum zinc voltaic cell. We're going to write and add the two half reactions, we're going to calculate the E0, we're going to write the line notation, and go on and on and on. So first of all, a voltaic cell. So you got two beakers, and each beaker has a chunk of metal, a metal strip of some sort in it. Each beaker has some sort of aqueous solution, and the metals are connected by a wire. That wire usually goes through a voltmeter, and the voltmeter is not a battery. I'm going to make that a prettier voltmeter. The voltmeter is not a battery, but it will show if electricity is going through. So essentially it would be like hooking it up to a light bulb and seeing if the light bulb lights. Also, to make this a good circuit, it needs to be complete, so we're going to add a salt bridge in there. So this is a salt bridge. Alright, so then on the left-hand side, typically I'll put oxidation, but the oxidation does not have to be on the left. On the right-hand side, I'll put reduction, but reduction does not have to be on the right. Since this is two beakers, you could definitely flip it. The oxidation side is called the anode. The reduction side is called the cathode. Let me label this salt bridge. So that is your generic voltaic cell. So now we're going to put zinc and aluminum into this voltaic cell. So check out your reduction potential chart and look and see who's higher, zinc or aluminum. And it looks to me like zinc is higher up on the list. Zn plus 2 electrons turns into Zn0. And aluminum is lower down on the list, so aluminum is the one that's going to be reversed. Al turns into Al plus 3 electrons. So those are my two half reactions. I flipped aluminum because aluminum is lower on the list than zinc, so aluminum is more easily oxidized than reduced. So if I put aluminum as the oxidation, then that means over here, this is a chunk of aluminum metal, maybe a piece of aluminum foil, and the liquid is aluminum ion in solution. And then the reduction side, this is a chunk of zinc metal, and the liquid is zinc ion in solution. So maybe that's aluminum sulfate and zinc nitrate or something along those lines. Okay, so aluminum is the thing that's going to be oxidized, which means the Al is turning into Al plus 3, and it's also losing electrons. So the electrons are going away from the Al up across the wire. On the other side, your zinc plus 2 is turning into Zn, and the reason why it's doing that is because electrons are coming across the wire, and the positive zinc ions are attracted to the negative electrons. In order to keep the whole thing neutral, positive ions from the salt bridge are going to go the same direction as the electrons, because it's getting a whole bunch of negative electrons, so it wants to get some positive ions. I'll make that a prettier looking arrow. And then the negative ions are going to go the other direction across the salt bridge, because it's losing all its negatives. In order to keep it neutral, it needs to get some negative ions. So, for example, if this was sodium and chlorine, the chlorines would be going left, and the sodiums would be going right. All right. And I think that's it for my picture. So I've got my two half reactions, so now I need to add the two half reactions together and figure out how much voltage this battery is going to give me. Well, notice that I cannot cancel the electrons because I have 3 and 2, and 3 and 2 don't cancel. So I'm going to multiply this entire zinc by 3 and the entire aluminum by 2, which will give me 6 electrons in both cases, 3 zincs, 2 aluminums, and now the 6 electrons will cancel. What I have left is 3 Zn plus 2 and 2 aluminums will make 3 Zn and 2 aluminum plus 3s. So there's my add the two half reactions together. Now I need the E0. From the chart, the zinc, which was higher up on the list, stayed like it was. So the zinc was a negative 0.76 volts. But the aluminum, which was lower down on the list, got flipped. And so the aluminum was a negative 1.66 volts. But since it got flipped, it's going to be a positive 1.66 volts. You do not have to multiply each of those numbers by 3 or by 2 because I multiply by those numbers in the balanced equation. Do not mess with the numbers other than to change the sign positive, negative. That's it. So your voltage is just add them together. 1.66 plus negative 0.76 is 0.0, no, that's not it, 0.9 volts. That's the voltage going through a battery. Last thing is the line notation. I'm going to erase that, and I'm going to put the line notation up there in the corner. The line notation is what's happening in this reaction going from left to right, starting at oxidation, ending at reduction. So we have, on the left, aluminum slash turning into Al plus 3, double slash. In the other beaker, we have Zn plus 2 slash turning into Zn. And that is my line notation. The line notation will always start with oxidation on the left and reduction on the right, even though in your picture you might have it flipped. Let's do another one. We've got a silver-zinc voltaic cell. We're going to write the two half reactions and the balanced equation. Notice this one does not say to diagram the cell, so I'm not going to bother with that. So, looking on your chart, you're looking for silver and you're looking for zinc. Who's higher? Silver. Silver's higher. So silver gets the number on the chart exactly as written, and it gets the equation on the chart exactly as written. That silver is a 0.80 volts. Zinc is lower on the chart, so zinc is going to get flipped. Zn turns into Zn plus 2 electrons. And on the chart, that is a negative 0.76, but since we're going to flip it, we'll make it a positive 0.76. So if we're going to add the half reactions together, notice that your electrons do not cancel unless you multiply all of the silver things by 2. So, I'm sorry, yeah, that's right. Oops, goodness gracious. Let's do that here. The 2 electrons will cancel, so I end up with 2Ag plus and Zn turns into 2Ag and Zn plus 2. That's your overall reaction. To get your voltage, add these two numbers, 0.8 and 0.76 is 1.56 volts. And then finally your line notation will always start with oxidation, and then it's just what's happening in each beaker. So on the oxidation side we have Zn turning into Zn plus 2, slash slash. On the reduction side we have Ag plus turning into Ag, and that's your line notation. What about a voltaic cell involving a solution? So we got silver and iron. These reduction reactions are written exactly from the chart, but one of them's going to have to get flipped. So notice that iron is lower down on your chart than silver is, so iron is the oxidation, not reduction. And this is asking for my E0, so I'm going to take the iron. On the chart, it's a positive 0.77, but since we flipped it, we're going to make it a negative 0.77. Silver from the chart exactly as written is a positive 0.8. So my voltage plus 0.8 minus 0.77 is equal to 0.03 volts. So I would say that that's probably not a very good battery. All right, let's diagram this cell. That means draw a picture of your cell. We got 2 beakers, and each one of these beakers has a chunk of metal in it, and those metals are connected along a wire to a voltmeter to prove that electricity is going through. There's a salt bridge, there's some sort of aqueous solution, and here, and the voltmeter has a V on it, and I'm going to call this SB for salt bridge. I'm going to put the oxidation on the left, that is the anode, and reduction on the right, that is the cathode. You do not have to do it that way. You could put reduction on the left and oxidation on the right. Doesn't really matter either way. If I put oxidation on the left, oxidation is loss of electrons, so the electrons are going to go across the wire left to right instead of right to left, which is totally fine. If you flip it, then make the electrons go the other direction. Now look up here, we had iron is the one that we flipped, so iron was the oxidation side, but also we have iron +2 and iron +3. When it has a charge like that, that is an aqueous solution, not a metal. So where are we going to put a metal? Like, what is the metal that's going to be connected to my wire over here? So check out your line notation. It has PT for platinum. So this piece of metal is a piece of platinum. And in your solution, you have Fe+2 and Fe+3. Those things are both just floating around in that solution, not the metal itself. That's not a piece of iron metal. So also see that Fe+2 comes before Fe+3, so this reaction will be going that direction. They always put it in the order of way it's happening. So that's oxidation. So the electron is coming off the Fe+2 and going on to that platinum, and then from the platinum it's going across the wire. In the other half cell, we have Ag+ turning into Ag, which means Ag+ is my solution. This is a chunk of silver metal, and the Ag+ will be turning into Ag. And that kind of looks like how your half reactions looked earlier. Ag+ turns into Ag, and Fe+2 turns into Fe+3. So we've got electron flow, cathode, anode, electrodes, and solution, and that is what an voltaic cell is with a solution, that you have an inert platinum metal, and all of your ions are just in the solution. So we're going to do another one that has hydrogen gas in it. I'm going to diagram the voltaic cell. Kind of as I'm working, I'll do the half reactions. My voltaic cell is going to start like every other voltaic cell starts, with a salt bridge and 2 metals connected across a wire with a voltmeter and some aqueous solutions. Let's see. Okay, I'm going to put oxidation with the anode on the right and reduction with the cathode on the left. By the way I remember that, anode, oxidation, reduction, cathode, and ox, red cat. You can't have and cat. I guess you could have red ox, but that's just reduction oxidation. Alright, so now, based on this line notation, the oxidation will be zinc turning into Zinc+2. So zinc metal will turn into Zn+2. Since I put oxidation on the left, and oxidation is the loss of electrons, the electrons are going to be going away from that Zn. On the other side, we'll have reduction, so the electrons are going to be coming in. We have H+ turning into H2. So H+ is your solution, and H2. Well, H2 is a gas, it's not a metal. So it's not like I have H2 metal chunk sitting here. That doesn't even make sense. How can I have an H2 metal chunk? So instead, what I have is some sort of like a cup, an upside down beaker or something that a wire can go through. So then that hydrogen turns into H2. The H2 is little bubbles of gas. They're going to be coming up out of this solution. And we're collecting them in a little cup, and those are little bubbles. And so then this metal here is platinum, PT metal, which is not actually reacting with anything. It's just an inert place for the electrons to collect, so the hydrogen ion can turn into hydrogen gas. So we're going to write the two half reactions. Over on the left, we have zinc turning into zinc plus 2. I got that straight from this line notation. I need 2 electrons on the right-hand side. Then the other one, we've got H plus turning into H2. That means I need 2 hydrogens and then 2 electrons to balance it. The electrons cancel, and then what's left over is Zn plus 2H plus makes Zn plus 2 plus H2. So that's my overall reaction. Now I need the E0. So the zinc is the one that's oxidized. That's going to go opposite of the reduction potential chart. So on the reduction potential chart, that is a negative 0.76. But since it's oxidation, we're going to make it a positive 0.76. The hydrogen will be exactly like it is on the reduction potential chart, which is 0. So negative 0.76 plus 0, positive 0.76 plus 0 is positive 0.76. So that's the voltage that we made out of this battery. One last voltaic cells. Okay, in a galvanic cell, remember galvanic, voltaic, same thing. Aqueous silver, that is Ag plus, since it's aqueous silver, is reduced by an unknown metal. The standard cell potential is found to be 0.47 volts. What's the reduction potential of the unknown metal? So I have Ag plus an electron turns into Ag. And according to the reduction potential chart, that's a 0.8 voltage. And then I have some unknown thing that produces an electron. It's the thing that's going to be oxidized and has some unknown voltage. And overall, the total voltage is 0.47 volts. So the question is, what is the voltage of this unknown thing? Okay, well, 0.8 plus what equals 0.47? 0.8 plus negative 0.33 is equal to 0.47. So what could this thing be, and what is the reduction potential? Well, since this number, negative 0.33, is how much you would get for oxidation, when you're looking on the chart, you're actually looking for something that has a positive 0.33 volts. That is its reduction potential. Let's try spelling that right. That is a positive number for its reduction potential. This negative number, the negative 0.33, is the oxidation potential with the electron on the right-hand side. Looking on your chart, the only thing I see is copper, which is a 0.34, so that's pretty close. And so that means that this reaction would probably be something like, that'd be copper. Cu turns into Cu plus 2 electrons. That means this would have to be doubled. Remember, that does not change the 0.8 even if you double it. And so that gives you your overall reaction with the electrons canceling. So the reduction potential here is a positive 0.33, even though to get it to fit in you needed a negative 0.33 because the negative is for the oxidation. All right, well, that's Voltaic Cells. I hope you had as much fun as I did. We'll see you next time.